In today's lesson, we're going to learn about Chapter 8, Section 1, Similar Polygons. So, in polygons, when we're talking about polygons, we've dealt with this before. We've talked about congruent polygons, and congruent polygons were polygons where corresponding parts were going to be equal. In a congruent polygon, all the angles and all the sides were equal to corresponding angles and sides of a second one. Similar is going to be similar to that, but similar polygons don't have both of those features. They have their unique features. So, for example, you have two shapes here. We have quadrilateral ABCD and quadrilateral MNOP. And we know, again, that, angle A is going to correspond with angle M. And in similar shapes, the corresponding angles are congruent. So angle A will equal whatever angle M equals. Angle B is going to be corresponding with angle N, and they are going to be congruent. Angle C goes with angle O, so C and O are corresponding and congruent. And then lastly, we have D and P, and we know that angle D and angle P are corresponding and also congruent. So this is similar to what you've done in the past with congruent polygons. The difference comes in when you're talking about the sides. In congruent shapes, the sides are exactly the same, but in similar polygons, what happens is the corresponding sides are proportionally equal to each other. However, they don't have the exact same unit of measure. So let me explain that. What happens is, for example, side AD corresponds with MP. And those two sides are going to have some proportional relation. Like, let's just say AD is 10 and MP is 5. If I was to try to figure out, well, what is that AD over MP? It's 10 over 5. So the relationship is a 2-to-1. That's also a scale factor, okay? And so that relationship is 2-to-1. So all the sides are going to have that same relationship. So what's going to happen here is AB corresponds with MN. So even though they're not going to have the same length, let's just say that the AB is 4 units long. We know that MN will be 2 units long. It's going to have that same 2-to-1 ratio, and so on and so forth. So if I go to BC, BC goes with NO, and let's say BC is 8 units, I know NO will be 4, and the same relationship will happen with CD and OP. And so what happens is that they will be proportionally similar, not numerically equal, but proportionally equal. So that scale factor that we talked about in that last slide, that's what this slide refers to. So if two polygons are similar, they have a scale factor, and the scale factor is the ratio of the corresponding sides of the two shapes. So in this particular problem, I can identify the scale factor. First of all, this is 2 equilateral triangles. So let's say AB might go with DF. And so I've got 3 to 6 or 1 to 2. So my scale factor, if I put the small one, let's say the small triangle over the large triangle, then the scale factor of small over large is going to be 3 to 6 or 1 to 2. Now, if I go in the other order, if I say, well, what's the scale factor of the large over small? It's going to be 6 to 3 or 2 to 1. Now, we're going to use that scale factor mathematically to solve some problems, but what we're going to have to do, first of all, is we're going to have to figure out, is there an order that they want? Do they want a half or 2 over 1, or do they not care the order? Usually, the book will do a drawing, and I'll show you what I mean in hopefully a subsequent example. So When we're trying to find scale factor of a problem, right, we need to know if the order matters, right? Does it matter which one I put up top? Does it matter which one I put at the bottom? And so in this problem, notice that it says find the scale factor of A, B, C, D to M, N, O, P. So from this large one on the left to the one on the right. And so yes, you have this original that you started with, and then you have like this new one that it changed to. Well, when you're looking for your scale factor, it's going to be the new one over the original, okay? So in this particular case, I have to find two corresponding sides on the two triangles, right? And try to find their scale factor. So I'm going to start with, notice the only side I have in the second triangle is MP. And I know that MP, right, corresponds with AD. So that's this side. So since they go together, I know my scale factor is going to be MP over AD. MP is 8, AD is 10, and when I simplify that, I get 4/5. And so my scale factor equals 4/5. Okay? Now that I know my scale factor is 4/5, well, I can use that scale factor to find all the other sides using these corresponding sides and the scale factor, and I'll show you. For example, I know that side AB goes with side MN. So AB is here, and it corresponds with side MN. So I know that this scale factor, 4/5, is going to be the same scale factor for MN over AB. So let's say MN is Y and AB is 12. And now, because I know they're equal, proportionally equal, I can use proportional math, which means I can use my cross products. I can do 5y equals 4 times 12, and then I can divide both sides by 5, and that's going to give me that y equals 48 over 5, or 9 3/5. So I know that y equals 9 3/5. Then I continue and I do the next one. So I know, for example, BC goes with NO. So I'm going to do, again, I know 4/5 is my scale factor. I know that NO over BC are going to have that same ratio, right? So 4/5 equals NO over BC, and I know that I'm going to use cross products. So 5x equals 16, and x equals 16 over 5, or x equals 3 1/5. So x is 3 1/5. And then I'm ready to do my last side, DC. I know DC corresponds with PO or OP, right? DC and OP. And again, I'm going to use that same scale factor. So I know if I do OP over CD, that's how I set it up. So OP is Z and DC is 14, and I use my cross products. So 5Z equals 56, and divide both sides by 5, and I get Z equals 11 1/5. Now, of course, they couldn't give it to us easy. They had to give us fractions. But again, we still were able to find the values, okay, of X, Y, and Z. Second, now it wants you to know what is the perimeter of each shape. Well, the perimeter of ABCD is the sum of all four sides, right? So 14 plus 4 plus 12 plus 10. So 18 plus 22, and it's going to be 40. So the perimeter is 40. Now, I can add up all those other fractions on the other side, but one interesting feature is that, well, I'll show you. You'll see now. I'll show you what I mean. Let's come through here and let's just do the math, right? So we've got 8 plus 9 3/5 plus 3 1/5 plus 11 1/5. And so I'm going to get 3/5 plus 1 is 5/5. And 9 plus 3 is 12. 12 and 1 is 23. So 23 and 5/5 is the same as 24. And so I'm going to get 32. So the perimeter of this second shape is 32. Now I want you to see something interesting, right? So P equals 40 and P equals 32. Now the last question asks us for the ratio of the perimeters. So again, we're going to do the new one. The perimeter of the new one is 32 over the perimeter of the original is 40. And guess what? That also simplifies to 4/5. So the scale factor of the sides is actually equal to the scale factor of the perimeters. So it's the same 4/5 as the sides. It's kind of an interesting relationship. So we didn't even really have to add all this up to know what the perimeter was. Once we knew the perimeter of the first one was 40, we could have done the same thing and made the perimeter of the second one x. And when we do the math, we would have gotten 160 equals 5x. And when we divided by 5, we would have gotten that x was 32, which was the perimeter. So you can use scale factor for perimeter as well. This slide here just reinforces what we've talked about. It just basically says that if you know two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. That's the strategy and the skill that we used in the last few slides. So now we come here and we're like, okay, what about this diagram? We've got triangle TPR is similar to XPZ. And so we know the two triangles are similar. Find the length of the altitude PS. Well, guess what? Altitudes also have the same scale factor. So, for example, we know that TR is going to be similar to XZ, right? So let's put the length of XZ up top, and let's put TR on the bottom. And the length of XZ is 16, and the length of TR is 12. Well, if I simplify that, I know that that simplifies to 4/3. So I know the scale factor, right, of the small one to the big one. Let's put big up top. And I did big over small, okay? Or right over left, however you want to do it, but I had that relationship. So now if I'm trying to use that scale factor to find, let's say, this missing piece, let's call it X, right, that missing altitude that I'm looking for, then I'm going to use the same ratio. I'm going to put the one on the right, or the bigger altitude, over the smaller altitude. And again, I'm going to just do the math. So 4x equals 20 times 3. 4x equals 60. And if I divide both sides by 4, I'm going to get that x equals 15. So I know that PS equals 15 units. So I can use the same scale factor and what I know about the corresponding parts and lengths, I can use it to solve any of these problems. So like we talked about before, the side lengths have a certain scale factor. Well, the perimeters have that same exact scale factor or ratio. So when it comes to areas, the scale factor relationship is interesting. So what happens is, let's say we have a scale factor of 1 to 2 on the sides, right? Well, then the scale factor of the perimeters, right, is going to be the same 1 to 2. Now, the scale factor of the areas is going to be whatever that scale factor is of the sides or the perimeter, whatever those ratios are, it's going to be squared. So it's going to be 1 to 4. So let's tackle a problem and see how that applies. Now notice here we've got this diagram. GHJK is similar to quadrilateral LMNP. Find the area of LMNP. Well, first of all, we know the area of GHJK, right? Well, let's figure out what is the scale factor first of something, right? Well, notice we've got kj, which we know kj goes with np or pn, so we know that these two sides are corresponding. So we know their ratios. If we go, let's say, the small one up top and the big one at the bottom, we know that the scale factor is 7 to 20, or the side lengths are 7 to 21, giving us a scale factor of 1 to 3, or 1/3. Well, that means that the areas are going to have a ratio of that 1/3 squared, or 1/9. So 1/9 is the fraction that I'm going to use in my proportional relationship. The area of the small, so small goes up top, over the area of the big, which again, I don't know. I'm going to make the area x, right? And I know that if I use my cross products, I'm going to figure out what it is. So 1x equals 84 times 9. So x is 36, carry the 3, 756. So I know 756 meters squared is the area of my large shape. In other words, it's 9 times the area of the shape of the smaller shape, because again, the scale factor or the relationship is 1 to 9.